Then we owe so much to this man, Ilya Prigogine. He was the first to finally seriously start studying what is now generally referred to as non-equilibrium thermodynamics. He was given the Nobel Prize in chemistry on what's called dissipative structures in 1977 on this exact work. He's the author of dozens of books, and I've listed a few here. His main studies were of irreversible processes and self-organizing systems in nature. And he discovered that entropy can be delayed. And in spite of authoring more than a dozen books, receiving the Nobel Prize for his discoveries, and founding an institute to continue these studies, Prigogine's work remains relatively unknown. Here's a couple of good quotes by Prigogine. Equilibrium thermodynamics was an achievement of the 19th century. Non-equilibrium thermodynamics was developed in the 20th century. Okay, in other words, there's nothing wrong with the study of equilibrium thermodynamics, but let's be careful to understand that it's not the only thermodynamics out there. In other words, if we look at reversible processes and are looking at something that's oscillating between equilibrium points and always seeking a single equilibrium, that's fine. Those guys worked that out in the 1840s. That's the way it works, okay? I mean, if you want to know how long coffee will remain warm in a thermos, it's days, it's not a problem. But that has nothing to do with how energy, that's not the only, way it works. This is a much more interesting quote here. Contrary to what happens at equilibrium or near equilibrium, systems far from equilibrium do not conform to any minimum principle that is valid for functions of free energy or entropy production. This is by a Nobel Prize guy. Okay? Now, in this case, free energy, he means energy available from the environment. And entropy means energy permanently lost as unrecoverable. Okay? So the two fundamental principles that he talks about are energy organization and energy dissipation. Energy organization is any process that gathers energy from the general environment up to a level that's higher than the environment. And self-organization is recognized as a natural function of the environment. In other words, tornadoes. Hey, that's an energy level that's up above the environment. No one paid to make those, right? Nature can do this stuff, okay? But basically, any way that we organize energy to a higher level can be seen as a gain in the system, okay? For energy dissipations, it's simply the opposite. Any process that disperses energy from a higher level down to the general level of the environment, okay? And this can be recognized as the work done by a system. Now, just like Carnot said, we're not destroying the heat, we're just moving it from a high concentration to a lower concentration and extracting work from that, okay? But more importantly, we want to look at energy as the true dissipation as that energy which becomes irretrievably lost by the system. In other words, if we're running a mechanical machine, it's the friction in the bearings and stuff that turns into heat. We can't get that back, unless we're trying to produce heat. Okay? If we're trying to produce mechanical energy, then friction is an irretrievable loss. Okay? And so this isn't rocket science. It's pretty straightforward. But we have to be willing to define our terms properly. So let's take a look at an example of this type of thing. Okay? I'm sure many of you have had a desktop distiller. Okay? These are wonderful things. And so you just you put water in the boiler, and they put a pressure cap on there. And then it's got a heating element in here, and you plug into the wall, and it makes the meter turn really a lot. And the steam comes out through the little cooler, and then we take more power from the wall to run this little fan and blow all the heat out the top and condense the water, and then we get the distilled water. Okay? It works. You can get distilled water this way. But it's really expensive. Let's do it this way. This is a regenerative steam distiller. Put cold water in over here. It comes through here, it goes through a heat exchanger thing, it comes up to the top here and hits a little heating element right here, which will boil it. At which point, what happens is that the impurities drop down through here, and the steam goes up through this loop, and of course, we just happen to need the exact amount of heat that it's going to take to boil the next water is the heat that it's going to take to condense the steam. Gee, let's use that instead of from the wall, okay? So then we use the heat given back from the condensation process to preheat the water coming in, so that the amount of energy we actually have to apply here at our heating element is just the heat that was lost by inappropriate insulation and other inefficiencies of the heat exchange system. And so here, now we can make about 7 or 8 times more distilled water for the same amount of hour input. Okay? The heating element only adds the loss, that which was dissipated, and all other heat is exchanged with the incoming water. So what we see is that the ideas that have come forward from heat pumps in relationship to COP and everything aren't just related to those mechanisms, okay? There is a general principle here. So what we see is the idea that the energy used by a system or process, that is equivalent to the energy dissipated by that process, is completely incorrect. Energy can be reused. We just reuse the heat. Okay? It's fascinating what people have come to believe. They tell us in one sentence that energy cannot be created or destroyed. But the minute you've used it once, you have to pay for it again. Where did that go? Where did that energy that can't be destroyed go if I have to buy more? Why can't I use the... I mean, if I buy a metal fork, I can use that more than once. They want us to believe... See, they've overlaid an economic model on top of the physics. They want us to believe that all energy has the value of a plastic picnic fork. It's meant to be used once before you have to buy it again, okay? It's an economic model. It has nothing to do with physics. Okay, so what is the COP of a system? Okay? It's simply the preferred output of the system divided by what I put in. Okay? The user. So, in a typical thermodynamic efficiency of less than 100%, which is we'll call this a closed system, the COP is less than 1. Okay? And here's a fascinating thing that we can find here. So we've got the user putting in, okay? We've got the preferred output. This is what we can work with. And then there's always these little losses, whether it's, bearing friction, heat in the transistors, whatever it is, okay? So this is the classic energy efficiency model that we're told that all machines must conform to. What is fascinatingly contradicting here is that the input can reflect no commerce with the environment, while the output is always losing something to the environment. In other words, this isn't a closed system either. Everybody believes, hey, you're losing heat to the environment. You can't get that back. Well, if the machine has commerce with the environment, why can't my input have commerce with the environment? So the whole thing, this is the big argument where everybody's saying, the second law of thermodynamics says you can't have free energy. This is goofy. Their closed systems are open at the output side. Don't believe this junk. Okay. So this is the efficiency model that covers appliances such as refrigerators, air conditioners, and other heat pumps. Okay. So now we've got a user input. That's the energy we're going to use to run the compressor. We've got environmental heat coming into the system as well. We have losses in the system, which is the ordinary friction of the moving parts and all that kind of stuff. We've got the amount of heat we've moved out of our refrigerator, so our food gets to be cold, okay? And then we're dumping the heat out into the environment again, okay? So this is typical of a heat pump. And this is what we call a modern regenerative system with an open system with a COP of greater than 5. And so now what we're going to see is that environmental energy that was thrown away in the last model, we're going to see, just like in our distiller, we're going to take the heat that came out of there. We don't have to throw it to the environment again like the tabletop models. We can recover that and recycle it and put it back into the system, put it back into the process. So we can get more new energy from the environment. We can have our user inputs, and we can recover energy that wasn't consumed by the process but simply used by the process. We're going to have our standard losses as usual, and we're going to have our preferred outputs. Okay? This is exactly the kind of thing that Paul Babcock was talking about yesterday, these types of models. Then we owe so much to this man, Ilya Prigogine. He was the first to finally seriously start studying what is now generally referred to as non-equilibrium, and he discovered that entropy can be delayed. And in spite of authoring more than a dozen books, receiving the Nobel Prize for his discoveries, and founding an institute to continue these studies, Prigogine's work remains relatively unknown. Here's a couple of good quotes by Prigogine. Equilibrium thermodynamics was an achievement of the 19th century. Non-equilibrium thermodynamics was developed in the 20th century. Okay? In other words, there's nothing wrong with the study of equilibrium thermodynamics. But let's be careful to understand that it's not the only thermodynamics out there. In other words, if we look at reversible processes and are looking at something that's oscillating between equilibrium points and always seeking a single equilibrium, that's fine. Those guys worked that out in the 1840s. That's the way it works, okay? I mean, if you want to know how long coffee will remain warm in a thermos, it's days, It's not a problem. But that has nothing to do with how energy, that's not the only, way it works. This thermodynamics, he was given the Nobel Prize in chemistry on what's called dissipative structures in 1977 on this exact work. He's the author of dozens of books, and I've listed a few here. His main studies were of irreversible processes and self-organizing systems in nature.